Hello, everybody. Thank you all for being with us today. We are pleased to start the final event of the Nanostar project. And we are very happy to have an introduction of the project, Philippe Latte, who is the director for the space activities in Aerospace Valley, that will tell us a few words.
Hello, everybody. Thank you, Maud, and thank you, Maud, and all the team for all the work that has been done within this project. I would like to really to thank all the partners and for the quality of job that has been done during this year. And I would like to thank as well the Secretary of Sudway for its permanent support during the duration of this project and due to the difficulty of the situation, the general situation. Just briefly, I would like to emphasize about the importance of this project and more generally about the training of people, of young people for space activities, because we are now facing a revolution in space. You can see each day in television the new company, new project, and so on. So, and all the country now are engaged in this race of space, of course, with the planetary and so on project, but more and more with very economical goals. And in this race for developing new constellation, new satellites, new services, the importance of small satellites is very high, because with the technology moving, each year we can improve the level of performance of very small satellites. So everybody in the world now would like to develop their own satellites, their own constellation, etc. And in this race, it's very important one of the key issues is the capability to have very well-trained young people and very well-informed young people. This is why we have done this project to support the creation of a group, we can say, of university and schools dealing with this subject and putting together the efforts to optimize and to rationalize the effort, and it's very important at this time, because we need to be very attractive for young people. We need to have very well trained young people, in particular in space, and this is one of the key of competitivity of Europe in the coming years. So I think this project has reached its goals. So we are beginning to think about follow-on that could be much more integrated and maybe something much more developed. But we will discuss it, I feel, maybe during this afternoon. Okay, so I don't want to be too long, because the agenda is very dense. So thank you one more time, and I let the floor to Mr. Le Gall and Mrs. Roger for some words about Sudway program. Thank you very much, and good meeting this afternoon.
Thank you very much, Philippe. Isabelle and Alexandre, it's your time.
Okay, thank you. Thank you, Maud. Thank you, Philippe. Good morning, everybody. So from Santander, from the Joint Secretary of the program Sudway, we are very pleased to participate in this closing event of the Nanostar project. and thank the project partnership for the invitation, and mainly the lead partner, Aerospace Valley. From the beginning, this project drew our attention to its objective and expected results, and above all, to the concrete and active involvement of students in the plane activity that Philippe has just said before. Since the Joint Secretariat, we have closely followed the successes achieved, and in particular, Alexandre Legal, who was the project's interlocutor within the Secretariat. So I give him the floor. Alexandre?
Thank you, Isabelle. So good afternoon, everyone. Thanks very much for participating. Thank you for the invitation to this final event of Nanostar, which is co-financed by the Interact Sudoer program. I would just like to take the opportunity to remind you a little bit what the Interact Sudoer program does, what it is. So it's one of the many tools of the EU policy, the cohesion policy, which is actually the second largest policy of the European Union in financial terms. And its objective is to contribute to the territorial cooperation in this case, in the Southwest Europe area. It's one of the 15 transnational cooperation programs. There are also different programs from cross-border to inter-regional programs, and we are in a transnational program between Spain, France, Portugal, the UK for Gibraltar, and the Principality of Andorra. The aim of the Sudoer program is to foster development of the area through a series of initiatives, which are projects, just like Nanostar, in a series of different objectives: innovation, competitiveness of SMEs.
Alexandre,
Yeah?
sorry to interrupt. Sometimes it cuts a little bit. Maybe we can try to, without switching on our camera, if you can try and switch off your camera.
Okay, switch off. Yes.
Yes.
Better?
Let's try again. Not
Okay.
from the beginning. We understood what you said, but it
Yes.
gets a little. So maybe we'll try this like this. Thanks.
Thank you. So yeah, just the objectives of the program are in line, of course, with the objectives of the EU. They are innovation, competitiveness of SMEs, improvement of energetic efficiency, a better management of risks, and a better respect of cultural and natural heritage. And between the key economic sectors of Southwest Europe, of course, we can identify space and aeronautics as a very important sector, with several major clusters in cities throughout France, Spain, and Portugal. Thinking of Toulouse, of course, of Madrid, and other cities in Andalusia as well. So, of course, it's natural that this program supports many initiatives in this sector in order to encourage its sustainable development through innovation. And this we have done in several projects with different approaches. I would just like to mention quickly these approaches. We have dealt with technological matters in space industry through cutting-edge innovation by the promotion and use of additive manufacturing technologies for the production of metal aircraft parts. That was in Addispace, or cross-sector innovation between automotive industry and aerospace sector in a project called Aerocar. So, of course, these technological approaches are vital. But other approaches are not neglected by the Sudoer program. For instance, we try to let SMEs from other sectors, such as agriculture, environment, maritime activities, benefit from the dynamic of the space industry, and in particular from the use they can make of the space data. That's the case in Novexport, which is also led by the same lead beneficiary as in Nanostar. So thanks to this project, we hope that we will have a spillover effect of these space data from many SMEs in Southwest Europe, and that it will help them export in a better way. And another approach, and here we come to Nanostar, to the heart of Nanostar, I would say is the academic approach, because how could we strengthen this economic sector without training the future generation of employees, without training the students and helping them have the appropriate skills? So we think the authorities of the program, that the aerospace universities in Southwest Europe can only benefit from a stronger cooperation, which will help them reach excellence. And this is the aim of Nanostar. The project, I would say, has brought us some fresh air. It has focused on the future of the nanosatellite industry, on our students. And indeed, what better way is there to bring universities together than competitions with a common goal, competitions for students. So in addition to their classical education, and competitions focused on a theme which is very innovative and very attractive. It has been mentioned, small or nano satellites. I think when you are a student, what is more satisfactory than sending your own product, the product you have designed, into space? In the opinion of the authorities of the program, we would say there are several positive implications, potentially. First, increasing the quality of education in universities, thanks to very practical applications of the knowledge. Second, foster early collaboration with companies, and thus let the students have a better employability. Third, bring innovative proposals forward, and some of them we will have the chance to see today. That are really very innovative, I think. And lastly, foster practical collaboration between universities, very practical, including the creation of common tools and infrastructure. And I think we will talk about it as well. I'm thinking of the platform. So for all these reasons, we are convinced that Nanostar is a very good representative of what a program such as Interrex Sudoe can achieve. And therefore, we hope the benefits of the project will be perceived for a long time still. And for now, I'll leave you the floor, because we are really keen to discover in detail all the achievements of Nanostar. Thank you very much.
Okay, Alexandre. Yes, before concluding our intervention, I would like to inform you about, very briefly, about the future of the Sudoe program for the 21-27 programming period. As you could see on our website or in the newsletter we sent last week, the Sudoe 21-27 program has been in preparation since the end of last year. In this regard, we attach particular importance to the involvement of stakeholders in the definition of the future of the program and on the challenges to which it will have to respond. For this reason, a survey is online, and I invite you, all of you, to participate by sharing your comments and observations with us, which I'm sure will enrich the debate with your experience and all the things you did with Nanostar and with other European projects. So it's expected that the program will be sent to the European Commission at the end of the year, and hopefully it will be approved in early 2022. Therefore, we hope that the first call for project could be launched in a year's time, in spring 2022. That's all. That's what we wanted to share with you today. In conclusion, I would like to reiterate our congratulations of the work accomplished, and I hope that this Nanostar cooperation will allow all of you to move towards new horizons. So thank you very much for your invitation, and I wish you a good afternoon of work. Thank you.
Thank you very much, Isabelle, and thank you again, Alexandre, for your time, for this introduction, and for the good advice that you give to Nanostar. So we'll maybe think of working on the next project for next year. We have time to prepare, and we all keep in mind that there is a survey online. So if you want to see more projects by Nanostar to be alive next year and in the coming year, please fill in this survey. It's really important.
Yes.
Thank you both. Yes. Thank you, Philippe, as well, for being with us for this introduction. And I will now shortly introduce what was Nanostar, because we are doing the final event of Nanostar. So Nanostar is a project, as you know, that aims to train students with high-level skills in space and project engineering. And we aim at providing students with the experience of a real space engineering process, starting from the conception to the design, assembly, integration, testing, and finally documentation. So today we will present you the results of this project. And this project has been successfully run by a consortium of 2 aerospace clusters, so led by Aerospace Valley, and Madrid Aerospace Cluster in Spain, 7 universities, 3 in France, the Bordeaux INP in Aquitaine, ISAE Supero in Toulouse, the University of Montpellier, 2 Spanish universities, the University Polytechnic in Madrid, University Carlos III in Madrid as well, and 2 universities in Portugal, the University Beira Interior, and the Technical Institute in Lisbon. To drive this project, we also had the support of, I forgot to move on. We also had the support of the ESABIC Business Incubation Centers, the one from south of France, managed by Aerospace Valley, the one of Portugal, managed by the Institute Pedro Núñez, and the one of Spain, with the Foundation Madrid. This project lasted 40 months. We had the chance to have an extension due to the COVID situation that slowed down a little bit the activities, and it was structured into 5 work packages. So the first one is the list of the partners' resources, so what is involved, what is available in each of the universities involved in the project. The second one aimed at developing an infrastructure with collaborative tools, so we will present you this just after this short introduction. We also developed a robust work methodology to do all this. The work package 4 means to develop and manage competitions, in organizing challenges in between universities and students. And finally, work package 5 aimed at working with industry panels and also fostering in the future of Nanostar. So we already had the introduction of the Interact Sudway program that funded us within this project during the 40 months. The agenda for this afternoon. So we'll start first with the Nanostar Academy, explaining how the software works and the methodology. Then we'll have a huge focus on the challenges. The third session will be quite special because this morning we had the final challenges with 10 with 10 students, team students competing for the challenges, and we will announce the winners during a live session. And finally, we'll talk to you about the future of Nanostar. So to start the Nanostar Academy, I now invite Thibaut Gatteau from the ISAE Supero to switch on his camera. I'm gonna give you access.
Okay.
Yeah.
So I'm here. Thanks for letting me present that. So I'm going to present you here the Nanostar software suite development phase. So it was part of the work package 2. So I'm Thibaut Gatteau, from ISAE Supero. And the work package 2 have 2 leaders on it. It was the technical from Lisboa and with Paulo Oliveira and myself from Isaiah Supero. But I wanted also to mention that Lucien Senanesh from also Isaiah Supero worked a lot on this work package. It was not only our work, of course. This work package was also the development, or the whole partners were involved in these developments. I'm just citing the leaders here. So what was the NSS? So the Nanostar Software Suite designed for? It was to allow the students an easy way to do their preliminary design for CubeSats. So what basically was the preliminary design goal is to have to define, to pre-design some subsystems and the subsystems architecture. So at the end, you want some figures to have an idea if the mission is feasible or not. But it's not only technical. The preliminary design needs also a lot of communication, team management, and all of that. A lot of soft skills that are super important. So when we speak about preliminary design to students, they are expecting a super software to build their CubeSat or rocket or whatever. And in reality, what they have is a bit more sad. It's like a lot of spreadsheets with a lot of figures. But we wanted to go a bit beyond that, and that was also a goal for the NSS. It was really student oriented. For doing a preliminary design, it's fine to have software, but it's also fine to have methodology. So for that, we use concurrent design engineering. So basically, I will not go deep in that, but you create data models, you are going to share data models, you are going to reiterate over all these models to reach an optimal design for your CubeSat. And for the project, the question was, are we going to reuse an existing CDE? Are we going to adapt some libraries? What were we going to do? Maybe from MBSE discipline, maybe we can do things with that. So to answer that, I will count you the NSS story development. What we have, so first, we have in the literature, we found a lot of different software to work on preliminary design or subsystem on this preliminary design. So from the world, so you have to do a mission analysis, you have to work on the structure, on the dissipation budget, and so on. So for Nanostar, on the first state, we discovered that there were a very big consistency issue, but we have to provide our students like a list of software they can already work on the challenge they were beginning. So for them, we pre-select a set of different software, and we propose them to use them. And in parallel, we were going to work on the issue of consistency between the different software. The goal was really to allow them to do a preliminary design of a CubeSat it's student oriented one more time. And we want multiple access from multiple sites. So for example, students from Bordeaux should be able to work with students of Madrid with no frontier, basically. We are at the era of internet. We want to use databases rather than spreadsheets. That's the point. We can go back further if you want. And also something that was very important for us, it was to allow through the NSS a way for every member of an institute to use its own tool. For example, if I don't know if a partner wanted to use its own tool, it should be very easy to integrate with the software suite. For that, so it would be student friendly and most of all open source. So that's all. So everybody is involved in this process. One key issue was the consistency between data and all the submodels we have to develop. What were we going to do about that? But we already know that open source was a good idea, and respect of standards was also a very good idea to answer this issue. We had the idea of 3 different approaches. So the monolithic one, just building one software to do all, but it was too heavy with the consortium, like with the structure of our consortium, it was not very designed for. So maybe a decentralized approach, so each can develop part of the thing, but we still have a consistency, a big consistency issue between the different modules. So we focus on a mixed approach with a centralized database. Sorry, I have a phone ringing. I'm very sorry. I'm closing the door. The life of the COVID style. Sorry for that. So we have a centralized database that will handle the consistency issues and orbiting module around this database to work on the different submodules or on the different subsystem of the CubeSat. So we reached this kind of architecture with a centralized database, more or less. We had a pretty good idea of which software already exists and we wanted to use because they were very practical for the students. They were like, we know them, we have good feedbacks on them. It was, for example, IDM CIC. And Jean-Luc is going to talk about the future of IDM CIC in some minutes. We had the OREKit library for space mechanics and for the mission analysis. And we had other modules that we know well, and in particular also for the visualization, we know VTS from CNES that really was useful for our students, but still remaining. Remember the consistency checking issue and all the interface, of course, with the database. So what was the strategy for developing that? First, we basically we share between all the partners the different work to do on the modules, knowing that some of the modules were already developed. For the mission analysis, we have already OREKit, for example. For the mechanical architecture, we have IBM CIC, and so on. And we knew that there was work on the interface to do. So we decided at ISAE to focus more on the centralized database and the interface work, letting our partner to work on or on their specialty or on the modules they wanted to work on. So I'm not going to go deep in the development process. I will just summarize some modules we have reached with the partners. So first, the nanospace. Nanospace is quite of the core of the management of the whole NSS. It's behind that, like here you can see the web interface. So basically from a browser, from your computer, you can connect to the server and access that. What's the interest? You have a synthesis of the whole project. Like you can have it's a system engineer view. But behind you have the real databases that ensure that the consistency of data and so on. I will not go in technical details, but basically just you have to know that it's a web application architecture. It has a REST API, so you can easily connect third-party software. And the database has very interesting properties that allow, for example, concurrent access on it. That was a requirement for a Nanostar project. For the mission analysis, we wanted to use OREKit, but we need a front end for our students because it was easier for them for pedagogical purpose to have some nice interface. We choose a web front end. And we trust sales group, our subcontractor, to work on it. So they develop. They were very familiar with OREKit. So basically, we have the main interface. We define our mission, and what they have done, sales group, they make the front end part, but also the link with the backend, the OREKit library. We have done the link with the NSS centralized database, and we wanted to use VTS for visualization of the orbit. So they provide us this link with JSAT-Orb, and to get a nice visualization of the orbit. We don't reinvent things. We just use VTS from CNES that is very, very practical. It's exactly the job of this tool. the same, I apologize for the other partners. I will only present some of the models. So the activity profile that we like UC3M was responsible of this development. So the same, they took a subcontractor, INA Space, and the goal of the activity profile is the goal of the tool was to generate the activity profile of a mission, like a typical mission or a variant of the main mission. The main point to mention was the respect of the standards, so they should be compatible with other applications. What looks like, again, a very strong effort was done on the interface with the user. So basically, you represent your mission with it's a timeline with the different block represent the different mode of the satellite. Is it going to be like in communication mode, in science mode, in safe mode, because there is an issue? So we can show that, and we can handle it very well. You can move directly. I am sorry, I don't have time to make you a demo, but you can very easily manage the activity profile with a graphical interface. You have some features. For example, you have different. You can visualize the eclipses of the for the mission, and you will see that has some interest later. So. I will not mention all the features of the activity profile, but just the automatic generation of the feasibility of an activity profile for a mission. So what's the interest of this feature is to allow you to script when you, for example, when you have to regenerate the preliminary design, you go on different iteration, you can very quickly check if the mission is feasible with the other data you already have. And one last but not least point to mention is a link with VTS also. I already mentioned VTS with the mission analysis, but it's the activity profile is providing outputs that are compatible with VTS. So it's super consistent from a system point of view. One very short example, it's for example on the SSO orbit, so sun-synchronous orbit, you can see like a typical activity profile. On the you can see like the perfect synchronization between the eclipse and the eclipse mode, for example. It's why it's simple, but it's super interesting for our students, like to check the consistency of the mission. It's very useful from a system point of view. So I will not go over all the models, but basically from a state like a partial development state, we have almost reached. We were able to reach a full set. About the interface, I didn't mention it, but we provide with. I will go back a bit on Nanospace. With Nanospace, we provide also a way like an API with a REST API. We provide a way to Python API and Angular API that allow you to connect very easily to this interface. So from this state, we reach almost full developed software. And more interesting, I will focus on this architecture. That's the final architecture of NSS now. So we can, when you have the nanospace that ensures the consistency and the different modules orbiting around it. According to the number, you can say it's the degree of automatization you reach. That means with external application, you still can use the graphical user interface to enter manually data, but it's more interesting to script to automatically update all the values. And we can mention also the possibility to connect external stuff. So for IDM, CIC, for example, we needed to develop a small interface because IDM is not open source and is not multi-platform. So we had to be compatible with this architecture. We need to do a little development. Bordeaux INP has done it to be able to send data from IBM to the centralized database, basically. But yes. What you have to remember, it's in for NSS, it's very easy to integrate a third-party application. It's all open source and AGPL, well, except the software from CNES. But you can find all the code source here in this address. You have a test server if you want to try a Nanospace. it's not like, I confess, it's not that easy to deploy. You have a Docker version of many modules to ease the deployment, but it's not really done like it's done to be deployed by an IT team of a university, for example. It's not really it's not a standalone one application. You have an effort to do to choose also what you need a system engineer to choose what you are going to use, actually what kind of data you are going to share and so on. And future work include some event management and real mission example. So I don't think I will stop here. I don't think we have a lot of time for question mode. So I propose to directly go on the methodological the presentation on the methodology by Gustavo, if it's fine for you, Maud.
Okay. Well, good morning, everyone. First of all, thank you so much for this opportunity. My name is José Miguel Álvarez from the Universidad Politécnica de Madrid, and I was called to be the speaker for this topic, the development of a common methodology for the design of nanosatellites for the Nanostar consortium. Concretely, I am going to talk about the main activities developed in the work package 3, which is about setting up a common methodology in the nanosatellite environment to provide students with guidelines in their challenge and to unify all frameworks from the different universities and institutions which are part of the consortium. This work package 3 was divided into two main tasks. The first one, to collect an inventory of all main existing methodologies and frameworks. And from this inventory, as a second task, to develop a Nanostar methodology to establish the main steps, guides, and milestones for students, but also from the main components of the consortium. This inventory also works to assess the needs of each university and institution, both in terms of functionalities and collaborative tools. As a result, a report with the main existing methodologies was developed, as you can see in this figure. And in this report, 4 main groups were included. All methodologies based on the NASA system engineering approach, the methodologies based on the Agile approach, a family of methodologies from the IT sector, the CubeSat methodologies from the Aalborg universities, and a collection of all methodologies followed by the members of the consortium. The members were already mentioned, but you can see also in this figure too. To fulfill the main task of the work package 3.2, a methodology based on the system engineering approach found in the ACSS was proposed. Since all members were close to this approach, it was the easiest way to establish a common methodology in which all members can work without as much as difficulty. A web methodology repository was implemented with this new methodology, including some nanosite design guides. Even this methodology was implemented in a website just to be easily accessible to all students and all members. Here, from this point of the presentation, I'm going to show you some examples from the Nanostar documentation website. For example, here you can see the main page. You can see there are a lot of different sections. In the first step section, it includes a brief introduction to preliminary design of a space mission. It is include, for example, the introduction to the nanosite preliminary design and a description of CubeSat and nanosatellites. some classification and some specifications from CubeSat, and also the main CubeSat suppliers. From the management methodology section, it was include the system engineering summary from the ACSS, the definition of the concurrent engineering approach, but also including some typical design phases, some CDF guides to establish a proper preliminary design. And it was also include a description of this agile development, which can be implemented both with the concurrent engineering. The next section was the preliminary design, which includes the main subsystem in the design of the nanosatellite mission. It includes all the subsystems that may be involved in the design of a nanosatellite. For example, if we select the attitude determination and control subsystem, there are some steps in the attitude design, the control modes and some guides to establish the spacecraft control type, including the passive control and active. Also a guide to size all the disturbance that may appear in the nanosatellite environment with all formulas and definitions. Also a guide to the selection and sizing of the concrete IDCS components, which means all the actuators and sensors also, which can be defined in this subsystem. We also include some useful tools that may help students in the preliminary design in their challenge. For example, we include some remote repositories, some file sources coding, also at GitHub, Google Drive. I mean, there are tools from which we are very familiar, but we think that it could be easy to students to have all of them collected in one site. Questionnaires were sent to the participating students to obtain some feedback, and from these questionnaires, there was a section about the methodology website. We use these answers to improve the website after every challenge using the comments from the students. For example, at the first after the first and after the second challenge, the students were asked if they had used the methodology, and as you can see, there was a plenty 93% in both challenge of people that they do use this methodology page. After the first challenge, students were also asked to rank these sections. Here I only presented the first three ones, which was the preliminary design, the first step, and the management methodology. From these answers, we can conclude that in some way students rank better these sections we were close to the concrete preliminary design. I mean, these parts which are more difficult or are more technical in engineering point of view. Finally, students were asked about some ideas of how to improve the methodology page of Nanostar. Here we include some of the answers. For example, more explanatory videos and pictures, more specific comments in some subsystems. For example, there are a lot of oh, I missed this slide, sorry. students were asked to tell which part of the methodology were most least useful. It's not the same as the last slide, because here we can include the answer more in detail. For example, the preliminary design, but concretely the EPS or the IDT section. Also, the wide range of websites to look the CubeSat components. And for the other part, the least useful were some of the parts of the preliminary design, concretely the communication section and the structure section, and the ACC standard, which means that at this point of view from the student in a preliminary design, maybe looking at the standards were too complicated or not as useful as some direct guides. And as I was saying, we asked for some ideas how to improve. For example, the more specific contents were mentioned because of these subsections, communication and structure, but they also mention about clarify some formulas or include this milestone from the preliminary design, which was included in the second section, the methodology part. And all of the comments were more or less implemented depending on the answer in order to improve this Nanostar methodology. And that's all for my part. Thank you so much. And if you have any question, do not hesitate.
Thank you very much, José Miguel. We will take the question after the next presentation on this subject. So okay. We are now very happy to have with us today Jean-Luc Legal, working for the CNES in France, and who has been involved in the project development since its beginning. So Jean-Luc, thank you for being with us today.
Thank you very much for giving me the opportunity to present the evolutions of our tools. I will be very quick. First of all, on my side, the Nanostar project was the organizations of more than 10 on-site seminars to present and learn about the IDEM modules. So thank you very much for your welcome in your university. It was a great pleasure to meet you, and it was good time before the COVID. Now, I just would like to come back and give you an overview of our approach, which is based on modular, on the standard database. Our approach is based to set up a reference model. So we use two main software, SimusAC to describe orbit and attitudes, and based on the standards, with VTS for visualizations of the results, and IDM CIC construction game to build a satellite and to produce the mass, power budget, and all the system budgets. So I just have here some notes on the evolutions of the tools. The first one is SimusAC. So we improve the capability of the software with new criteria to define attitude conditions. So now we have some orbit number, longitude, latitude as a condition. We also improve the management of relying to impose an attitude and to manage to improve the management of the slew modes. We had in SimusAC publications of ephemeris and dedicated to link budget. So now we had systematically the some ephemeris dedicated to the satellite directions in the ground station, or the ground station's directions in the sensor, in the antenna frame, or in the satellite frame. We also have the ability to write scripts in a Scilab, and the software is now available on internet. So you have the address here, and you can download the software, which is free. You can download on the website of CNES. For IDM-CIC, the main evolutions is a new viewer, 3D viewer, integrated in IDM-CIC. We have now an alternative to SketchUp, because we use SketchUp at the beginning, and now we keep the two software. But with IDM-CAD, we have improvement of performance, and we have a capability of step visualizations. So I propose to show you a small demonstrations, just to, I don't know if it's okay for you here.
Yes, we can see the screen.
You can see my satellite?
Yeah, exactly.
Okay, so it's ISAT Nanosat satellite. And you can see here the visualizations, this 3D view. It's based on Open Cascade, and we have a capability of interactions now. You can see here the capability with dynamic visualizations. If I want to close or to open the panel, I also have the capabilities to explode the view. And you can see it's now we have a capability of dynamics. We also have a capability to import step parts, and you can see here, for example, the mechanism. It was import from design with CATIA, and from CATIA we perform step files, and here we have the capability, I think, to animate the mechanism, if you want to see the different filters of the wheels for this kind of mechanism. Okay, so I don't want to spend too much time. It was just the idea to show you the capability of, it's a main evolution for us to have IDM-CAD now available. We also have new capabilities for with new shapes to design with polyline or Bezier curves for trajectories, or to design some pipes. We also have the capabilities to mesh, of meshing. So we have a capability of meshing 2D shapes. So with these capabilities, you will see next we will have capabilities to perform a thermal model, or a model which requires meshing. We had the export in STL format, and we have with IDM View optimizations to load the CAD models, and to visualize capabilities to visualize the constellation. I would like, just before to finish, to mention that we also develop new models. IDM plot, a very simple model, but to display graphs, and very easy to use. We have developed Opalis. Opalis, it's an application to simulate a power supply chain composed of a solar array, a battery, and a regulation system. And the objective is to do a simulation of the electric behavior of a satellite, and we produce a depth of discharge of the battery and so on. We have a new one. It's a RF comlink module to simulate the telecommunication link from a satellite to ground stations. So The simulation consists to take into account a transmitter, the propagation characteristic, and a receiver, which can be the ground stations. And we have in progress 2 modules in development, IDEM thermal. So our objective is to have capabilities from IDEM CIC to produce a mesh onto the shapes, to manage materials, and to produce the step task files. Step task is standards to model thermal point of view of a satellite. And we also initialize the development of modules dedicated to ADCS, so for attitude and control system, with the idea to have the ability to precise the wheels of different parts of the different actuators of the satellite. So, but it's the beginning of this development. So, thank you very much to invite me today, and I will answer your questions with pleasure. And you can also contact me if any questions after this seminar.
Thank you very much, Jean-Luc. I think we can move on to the next session, which is the Nanostar Challenges. As we said before, the challenges was one of the main aspects of the project. And we will have a presentation here by, well, to start by several speakers, but we will start with Filippo Ciccocchi and Anthony Giotto, sorry. I'm about to give you access.
Okay, thank you very much, Maud. And it was a very nice presentation before. I wish we're going to do as well, Filippo. So we are going to deep within the challenges that we gave to the students. It was, let's say, one of the main part of that project. So that part was coordinated together with the University of Carlos III in Madrid, UC3M, and also Bordeaux INP. The main objectives of that, of the student challenge, was to provide a realistic test bench for the methodology and the software tools that were presented just before. Also, it was about training the first cohort of students from this Nanostar network, and to demonstrate a collaborative education model, taking the benefits of all the faculty that were involved and all the means and the personnel that were involved in the Nanostar project. So I'm moving to the next slide if it won't. Okay, it's working. So we've done basically we gave student challenges because it's part of the motivation to challenge them such that they provide the best of themselves. And we mainly provided them 3 different competitions. The first 2 were related to preliminary mission design that had to use the NSF software and especially the MCIC that was presented before, together with the methodology. So the first mission was a flyby to the moon, and the second one was about operating a nanosatellite for a biological payload that Filippo is going to detail later. And then we had some specific design, manufacturing and test challenges that we provided to the students. The first 2 preliminary missions were a unique competitive test bench, and they used the tools. So it was very nice for us that the students tried the tools, and we learned a lot from their feedbacks, and also those designs that they've done provided some, let's say, information that we fed to the specific challenges that we organized later on. The students for all those challenges were evaluated by a Nanostar jury panel with some winners that have been announced for the first two preliminary mission design. And we are going to announce the winner of the specific challenges later on this afternoon. And all of them received prizes and also some participation diploma to value the work they've done. So here is the timeline of the project. So I don't know if you see my, yeah, you can see. So we started first with the first preliminary design challenge. So here's the summer. Okay, we've done that challenge during one semester. So then we had the student had the holidays, and we prepared for the next challenge that also was about one semester. And in between, meanwhile, we also started some specific challenges. Of course, then we had the COVID that stopped most of the challenges that we were going on. Almost one semester was lost, and then we started again with those challenges. And we made some evaluation. We finished today, in fact, and we are about to end that project and continue and define how the Nanostar network will continue working on. Here is before I give the hand to Filippo. Here are let's say the numbers about those student challenging. So nearly about 300 students were involved. So that's about 70 teams that work on the different challenges. We have one winning competition design presentation at an international conference. The first pre-design challenge. The student made a great presentation in an international conference. All the partners got at least 2 seminaries per university, or at least 2 seminaries related to EDM-CIC, and I'd like to thank a lot Jean-Luc Le Gall that made those seminars, most of them. We have 21 suggested tools for the design, communication, and management. Many feedbacks from the students that help us improve our tools and softwares. And also, one nice event was the hackathon that was organized at UC3M, especially about the CubeSat altitude. So, Filippo, I give you the talk.
Okay, so thank you very much, Anthony, for this introduction. Let's see if my mouse works. So, okay, I see. Sorry, this is very quick. Okay, so let's go on with the first preliminary mission design. So this competition took place indeed in 2019 between in the second semester of the 2019 academic course. So between February and May 2019, with a duration of 3 months. And the objective of this mission was to design a nanosatellite that would reach the moon, starting from a given initial orbit around the Earth, and in order to observe with an optical camera and possibly also some spectrometer the surface of the moon in search for water ice. Okay, so this was the statement that we announced for this competition, and we had a quite large number of competing teams. So we had 15 teams from 6 different universities of the consortium. And there was a winning team, of course, and it's the UB Moon Invaders team that will be interviewed in half an hour, so during this very same session. And it is their work that was indeed presented at an international conference, as just mentioned by Anthony. And this was the third symposium on space educational activities in Leicester in 2019. Here you can see an image taken from their analysis of the flyby trajectory studied, analyzed by the Moon Invaders teams to first observe the Moon during the first flyby. Actually, some additional maneuvers were performed later for an orbit insertion. But this that is shown here in the slide is the first flyby, or the first pass over the Moon's surface. Of course, there were also other very good designs. One of them, the mechanical design of the satellite made by CubeSat chefs, was taken as a manufacturing a specific challenge goal, which was to manufacture a simplified model of the designed satellite. So this was the design made by the CubeSat chefs team, and one specific challenge focused on 3D printing this very same satellite. So you can see here that we went from a CAD model, a 3D model, to a real 3D printed simplified model or mock-up of the satellite. Of course, this is just a demonstrative model, so it does not contain the real equipment, okay? But in any case, it's very interesting to see something that goes from scratch to a real implementation with the manufacturing process. Going now to the second preliminary mission design, this focused on the in-orbit demonstration of a biological payload that will be introduced in a moment by Olivier and Xavier, okay? However, the mission statement was to demonstrate the successful in-orbit operations of a biological payload that contained Roscoff worms. These are worms that receiving light from the sun, they are capable of generating oxygen. So they are a very good candidate for life support systems in exploration manned mission. Okay. So it is very interesting to demonstrate their survivability in space with inside a nanosatellite, okay? So in this case, we had 6 teams that completed the challenge. Actually, more of them participated, but due to the strict deadlines, not all of them were able to complete their work. The winner was UC3M Starworms, that will be interviewed later. And this competition also fueled a specific challenge on the design of the Roscoff worms detection. Okay, so there will be later on a presentation on the detection system of Roscoff worms within the Roscoff worms payload. Okay, and here you can see a picture of the design of the winning design of this competition. Coming now to the detailed design and analysis challenges. This started in September 2019. They lasted 1.5 years, and they can be divided in 4 different types. So there were challenges related to the design of a component of a nanosatellite, other challenges dedicated to the analysis of relevant problems relevant to the nanosatellite's world, okay? And then others dedicated to real manufacturing or in-scale reproduction of a relevant component or system of a nanosatellite. And finally, other challenges related to the testing of some type of infrastructure, hardware, or algorithm, of course, of interest for nanosatellites. With these challenges, we actually completed 49 challenges across the 6 different institutions. We covered a lot of relevant areas of a complete nanosatellite system. So what is important to say is that this work can constitute kind of a bibliography for future work in nanosatellite, because a lot of areas have been covered, okay? And you can find relevant information about each one of these challenges at this link. It's in the Nanostar official website. And we can see here a screenshot of how this webpage looks like. So here you see only 8 challenges out of the 49 that have been completed. And you can also sort the challenges by institution, selecting the university at which they were carried out, okay? Finally, we have a look at all the areas that have been covered with these relevant challenges. We can see here the satellite, the life support system, and also ground equipment. We had challenges on all the relevant subsystem of a satellite, starting from propulsion, covering also structures. From the point of view of manufacturing and simulations, we had a challenge regarding the payload, which in this case is the Roscoff worms. We had challenges on the electric power subsystem, on the attitude determination and control subsystem, on the communications. But also we had the challenges on ground testing. So 2 challenges on vacuum testing and 1 on plasma environment testing for nanosatellites. We had challenges on ground stations. Of course, we have had 3 of them across the consortium. 6 challenges on preliminary design and concurrent engineering, so on software for mission pre-design. And also 1 challenge regarding the launch segment, okay? And this consisted in the development of a rocket test platform for nanosatellite components. And finally, 2 additional challenges on life support systems, okay? With this, I conclude my talk, and we give a word to Xavier Bailey, who will introduce the Roscoff worms project from its very genesis, and Olivier Marty will talk about the.
If you really want to have on board the living biological species, this implies, of course, to control life cycle in captivity under the space or the drastic space conditions. In other words, the idea is to be able to establish robust bioregenerative life support systems. So I had this I was pretty lucky working with Olivier Marty to not to supervise, but at least to give the possibility to a group of students to think and work about this idea in order to evaluate the biological properties of this photosymbiotic system in the context or in the frame of space exploration. And as you will see very quickly, because Olivier will specifically speak about that, the idea was to evaluate the technological constraint of a worm colony as a payload, and Olivier will tell you much more details about that. In other words, it consists in trying to control all the parameters, all the key and vital pivotal parameters for maintaining alive such a colony of worms, able to produce oxygen, recycle CO2, maybe provide food, and recycle metabolic waste. And second aspect of the challenge is to have a clear idea of the health of worm colonies in space. In other words, to have a functional remote system for the observation of the worms, how they survive, how they reproduce, do they continue to produce actively oxygen, and so on. And this has been done with a second group of students using artificial intelligence combined with neural networks in order to help to visualize and observe worms in space.
My name is Olivier Marty. At the time of the project, the Nanostar project, I was working for Bordeaux INP, and I was with Xavier writing the specification of the payload challenge. And the idea was, as Xavier explained, why do we need to send Roscoff worms in space? One of the topics was to answer the question, okay, we need to provide some tools for the astronauts to be able to recycle their oxygen and their metabolic waste, and as well to feed them. And that means that we had the idea to design a payload for the nanosatellites that is able to at least not do all of that, at least to recycle the oxygen, the CO2 into oxygen. And that means that the payload needs artificial light, pumps, microfluidic pumps, probes, heating, ADCS, SATCOM with the band S at least, and as we will see later on, computer vision. This is just a bestiary of several nanosatellites that do exist already. Some of them have been already launched by the NASA. Some of them are being built by the Montpellier Space Center at the moment. Some of them are projects of ESA and private companies and universities like MEDISA. The difference in between them is just what we put in these nanosatellites, but it's always living forms. Should it be bacteria, antifungal agent, organic molecules, plant cells, spirulina, or fish eggs for the last one. And what we aim to do with Xavier is to send in space the Roscoe worms. And if you want some more details about what has been achieved so far in the other nanosatellites, okay, on the left top corner, you got what is actually in the ISS, which is the Advanced Closed Loop System, a life support system. This is the brand new one that is shipped already. That is several details on the lab on a chip, the bio CDs, as they call them, are embedded in the Spore lab, SporeSat lab on the nanosatellites. The Artemis device is part of the MEDISA project, big project, and this is a view on the right down corner, for instance, of a spirulina inside one of these photobioreactors. Oops. Okay, that was the end of it. Not on my slides at least, but whatever. So this is just a short presentation of what a photobioreactor in space could be. And of course, everything is to be done, and this is part of the project we've got with Xavier, and we speak about it for 2 years now. But it was part of the challenge of the students. That means that one of the challenge teams, but that was not presenting anything last year, but they had worked on that. And the genesis of that, maybe Xavier didn't tell it, was, or Anthony, because I missed the beginning of the presentation, but at the genesis of this, middle school students or pupils did work on the Roscoe worms already and had a test bench on some experience with Arduino board and something like that, and microfluidic pumps, just to show that it could work and we could have probes and so on. But of course, it wasn't supposed to be embedded yet on a nanosatellite. But that's EM. The EM and Xavier and I are speaking with all together and with the CNES to do what is possible. The next session was supposed to be presented by the students themselves, but they got other stuff to do, student stuff. They got an exam, I guess, now in cybersecurity, as far as I understood, so they cannot present it, so I will do it myself. One of the focus of this big project is to focus on the supervision of the health of the worms. That means that what they worked on is to be able to build a tool to help this supervision. Of course, we can supervise the probes, the pumps, the quality of the water. We can supervise monitoring and controlling everything like the temperature, the light, and we need to do it, of course. But one of the interesting part is how with just a camera we can assure that the worms are in good health. So these students focus with artificial intelligence and classical computer vision tricks to be able to achieve that. Just one comment on these three photographs. This is an adult worms. This is a juvenile, and this is a cluster of eggs. Xavier, correct me if I'm wrong.
There are embryos actually in these cocoons.
So the first approach is the machine learning. So the machine learning aims at training a neural network. This is just basically what they have done so far. They have videos, HD quality videos from Xavier. They slice the video into different pictures. They create bouncing boxes around the different elements they want the neural networks to be able to recognize afterwards. They manually have to label for that the pictures. This is called a supervised neural network. And then train with that a YOLO convolutional neural network, CNN, which is based on the data sets made out of that. And the first goal was to detect the worms at first, but then we need to be able to classify them by color, by size, by age, by behavior, by sexual maturity, by speed, by phototactism. This is the ability to follow the light. Which ones are in good health, bad health, etc. So far, nothing of all of that. Just one thing is done. It's they are able to detect them and to track them, to follow the movement of it and the colors, I guess, as well. The second approach is simpler. It's computer vision. They need a uniform black background. They need to contrast, to enhance the contrast with the histogram equalization. They need to correct the gamma, so the colorimetry. They need to play with the thresholding of the image binarization to be able to extract the worms. They isolate them by color, and they are able as well to track the trajectories, which is what is done here. So far they have done all of that. What I can present you is a quick overview of the results in terms of what is going better than the other with the two technologies, machine learning and the computer vision. In terms of is it easy to set up for each class of worms, is it easy to adapt to the new data sets with new worms, is it robust to the zoom of the growth of the worms, what about the performances, because one of the trick is to embed this in something like a Raspberry Pi small computer board. What about the performances with or without a GPU, a TPU? What about the false positive, the loose detection ratios, etc.? So some works needs to be done, but at least we got an overview of, okay, this is not perfect, and sometimes the machine learning is better. Sometimes the new horizons are what the students are working on at the very latest stage of the project. And of course, not all of them has been done. Okay, this is a video of the worms, if it works. So I will just finish with the fact that the last question is should we aim at compute everything on board on the nano satellites, or should we compute everything in the ground station? That means that we need to have a bargain in between the processing possibilities on board or the SATCOM possibilities. performances.
So thank you very much, Olivier and Xavier, for your very nice and interesting presentation about Roscoff worms. And indeed, the first interview of the winners of the second competition of preliminary mission design will be carried out by Anthony exactly on the winning team that designed the satellite that hosts such a worms payload. Okay, so Anthony, you can go ahead with the presentation well, actually we will have a short presentation by the students. So we are a Star Wars UC3 TM team, and we were the winners of the second edition of a space mission pre-design challenge together with the best PDR document. The team was formed by Álvaro Sanz, who was the team leader of the project and also was the project management and the system engineer. Miguel Renieblas, who was the responsible of the avionics and the mission analysis. Sergio Sarasola, who was responsible of the electric power subsystem. Miguel Muñoz, in charge of thermal subsystem, and myself, Álvaro Arroyo, who was responsible of the AOCS subsystem. So as we have here from Olivier, the goal of this mission was to verify the survivability in space of this marine photosymbiotic species of worms, the Roscoff worms, which may one day play an essential role in the creation of artificial ecosystem for deep space exploration missions. So the scientific payload will monitor the metabolism of these worms and their efficiency for urea and recycling via video observation and measurements. The payload of the mission was characterized by is a 3UL shape. As said before, the monitoring of the worms was made through cameras and sensors, and the required power was 9.5 watts, and the temperature range was between 11 and 15 Celsius. So in order to find the best solution of the mission, we perform a concurrent engineering process in order to check and analyze the relations between the different subsystems of the CubeSat, then derive the different requirements between them, and through this iteration, finally we obtain the most optimized concurrent design. We also perform trade-offs between the different components of the different subsystems to obtain those codes, the commercial off-the-shelf components, that could fit better in our design. And at the end, we thought that our solution was robust, mature, and reliable enough to be the starting point for more detailed design phases. In the pictures, you can see the 3D representations for our 6U CubeSat with the different components, the structure, some sensors, a sun tracker, magnet torquers, reaction wheels for the EOCS, the different antennas and the onboard computer for the avionics, and also the PDUs and the batteries for the power subsystem. And in the bottom left, you can see also the sonar panels in both retractor and deployed. And finally, this is in this last slide, we present a summary of the solution that we presented to the challenge. In the table of the right, we show an overview of the final solution with the different components chosen for the mission. As orbit, we select the sun-synchronous orbit at 500 kilometers. And the final mass we obtained was 15.77 kilograms, with taking into account different system margins. And as a final budget for the mission, we estimated 134.5 thousands of euros. So this is a brief summary of the solution that we presented to the challenge. And if you have any questions, so do not hesitate to ask.
Thank you very much. So I prepared some questions that I'd like to ask to you. So the design that you presented, the preliminary design, was really a collaborative concurrent engineering process. And I was wondering, what was the single aspect of this process that proved to be the most problematic?
Yeah, for the most problematic aspect of the concurrent engineering process was the the iteration of different requirements, you know, because from those already stated in the problem, to perform what to do this, that we have to decide which sections of the mission have to be relationed between them. From there, we think about the derivative requirements, so that finally all the requirements set out by Nanostar will be fulfilled. This is something we spend a lot of time and as we could have an initial idea that later then when we evaluated it, taking into account another analysis of another subsystem, we modified that what we have already done or allowed us to optimize what we have initially thought of.
Thank you. And I do have another question. Has this challenge provided you added value to your training in nanosatellites and curriculum? Why and how?
Well, yes, most of us had started the master's degree in space engineering at the UC3M, and it was quite a challenge as we had just started with the different studies related to space engineering. And thanks to the project, we gained a lot of experience with the different subsystems, which we will later see in the master's degree, which allowed us to win an internal university competition within the spacecraft design subject, which was another subject from the master program, in which we have to design a CubeSat for a real mission for the Mexican Space Agency.
Okay. And the last question. So you took part in this preliminary design competition in 2019-2020. What has been the impact of this competition so far on your job opportunities and/or assigned technical tasks?
Well, just after we were announced as the winners, one of our professors proposed us to present the project at their office at GMB, which is a very well-known company in the European and Spanish space industry sector. And yeah, most of us, we are currently working in the space sector. Alvaro Sanz, for example, is system engineering at OHB. Alvaro Arroyo is an space situational awareness engineer at Deimos. Miguel Renieblas is working in the flight dynamics division at GMB. And myself, I am the head of engineering in a small company, FOSA Systems, which is dedicated to the development and manufacturing of pico satellites for diverse applications.
Very nice. Thank you very much.
Thank you.
Thank you. So thank you very much. The next team to be interviewed is a team who participated also this morning to the final presentations of the specific challenges, and is represented today by Nigel and Johan. First of all, yeah, they are going to show you a short video.
Yes.
And then we.
So, can you hear me?
Yes, we can hear you.
Okay. So hello everybody, thanks for joining us today. So Johan and I will present you our project that is called the Air Balloon Project. So it's part of the Nanostar Challenges. So we are two students of Bordeaux INP at ENSA in France, an engineering school. And we worked on this project with 3 other students from our promotion within the past few months. So the main goal of the project was to release a sounding balloon in the stratosphere with onboard electronics and experiments, and to make sure that they are able to work in space conditions, so in terms of pressure or temperature. So the payload that we designed ourselves was made of 2 models. The first one was made for taking sensor data and sending to the ground with the LoRa protocol. And the second one was here to take photos and videos of the flights inside the payload gondola.
So yes, I will ask it to Nigel, and it regards the part of the challenge that proved to be the most difficult from both an organizational and technical point of view.
Okay, can you hear me?
Yes.
Okay, so I would say from an organizational point of view, the most difficult part was dealing with the deadlines and the planning, because the deadlines change a lot. For example, the liftoff was initially scheduled on April 2020, and finally it happened on January 2021, mostly because of the COVID-19, of course, but also there are factors that we can't control, like the weather and the pandemic, of course, and the effect that the pandemic has on the organization. So it's very important for this type of events. And also we had to study in parallel because we are all students in the team. So we had to study by one side and work on the project from the other side. So we had to find the time to work on the project and a day where everyone was available to make the launch. So it was very difficult because we had small opportunities to launch because of the COVID. So if we miss an opportunity, maybe we will not have another opportunity until 1 month or two. So we had to be very agile with the planning and the deadline. So to me, this was the most difficult part in terms of organization. From the technical point of view, I think the most difficult part was to make sure that the gondola and all the payload was meeting the requirements provided by the CNES and Planet Science. Otherwise, we wouldn't have been authorized to lift off, so it would be problematic. And also, we had to make sure that all the equipment was working in the space conditions. So, for example, in terms of temperature, the balloon reached 50 degrees under zero on the outside during its trip, so it was the coldest point. And generally, the electronic is not designed to support such temperatures, so we had to make sure that the setup was able to make the electronic works. And we also made reception tests to measure the maximum range, but it was theoretical, so we couldn't be sure at 100% that's what we're going to send into the air will work on the launch day. So this was difficult to make sure that this will work.
Okay, thank you very much. And the second question will be to Johan. Did you develop any complementary skills or improve them through your participation in this challenge? What would you say to other students who are thinking of joining future Nanostar challenges or future challenges like Nanostar one?
I would say go ahead, do not hesitate, because it's a unique opportunity to work on space study, because it's also an occasion to challenge yourself on a concrete project and on very demanding projects. This is related to space, because now we are living in such a fantastic period concerning space. Nowadays, there is space events every day. So, for example, the recent landing of Perseverance on Mars, the flight of Ingenuity, or even yesterday, the departure of the probe OSIRIS-REx from the Bennu asteroid that will bring samples of asteroids down to Earth, which, in my opinion, is just extraordinary. So it's the right time to jump in the train, otherwise it will be too late, because now things are going so fast that we can't wait to join the adventure. So taking part to a challenge like Nanostar is a unique opportunity somehow to take part to this great adventure that is waiting for us in the next few years. So do not hesitate. You will also develop new skills. You will improve your skills, and it's 100% worth it. So do not hesitate to join the adventure.
Okay, thank you. That's a good merchandising. It's a good publicity. Which complementary skills did you obtain or improve through the participation to this Nanostar challenge?
Okay, so as a student, I think that, well, it was for me and also probably for the other people in the team, the first time we were involved in such a big project. So with the goal of going almost from scratch to reaching the final goal that was quite ambitious. So we improved a lot in leading a project, and there it was quite a big one. So we improved in working as a team on different aspects. And about technical skills, it was my third project, for example, about IoT, and it uses a lot of different skills, such as coding an Arduino, finding the right sensors for the applications, and adapting them to our needs. And so all these things combined with dealing with space constraints with the temperature, pressure, and weight was really full of new skills and other skills improving. So that was really, really interesting.
Okay, thank you. Thank you very much, Johan, for your feedback and for your answer. So I think we can go ahead with the next student team to be interviewed, who is the winner of the first preliminary design competition. So Anthony, go ahead.
Yeah, so we are going to have an interview and a presentation from the student from UB related to the second student design challenge of a nanosatellite. It was for the study a flyby to the moon. So you have a short presentation, right?
Yes. Can you hear me?
Yes, we can hear you.
Presentation then. So hello everyone. My name is Pedro, and I'm here to present the winning project for the first edition of the Student Challenges, which was about a preliminary design of a microsatellite that performs flybys in the moon's south pole. This animation shows a well-studied trajectory for the satellite. It starts on a geostationary transfer orbit, then it performs burns on the perigee, making it propagate until it reaches the moon. It has been proven that there are ice crystals on the moon's poles, and the mission objective is to determine where exactly there's a bigger amount of water using spectrometers. Since it's a preliminary design, all the following subsystems were carefully analyzed. A thermal control subsystem consisting of a multi-layer insulation of Kapton and Millar, a mechanical structure that holds all of the subsystems, including the payload, a communication subsystem consisting of an antenna, a transmitter, and a GPS receiver, an electrical power subsystem that provides the satellite with energy through solar panels, an ADCS subsystem consisting of 4 reaction wheels, a chemical thruster to perform maneuvers, and the payload, which was already mentioned. Finally, this mission gives an innovative and low-cost solution for an interplanetary mission, demonstrating the capability of CubeSats. So this was the poster presented at the Space Symposium for Educational Activities at the University of Leicester, which we can go into detail later if anyone has some questions, for example. Here we have the members of the Moon Invaders team. If someone is interested in contacting any member, the LinkedIn contacts can be seen in the slide. So thank you. I would also like to take the liberty to thank the organizers of this event for the invitation, and to the Nanostar Consortium in general for the opportunity to take part in this project. I will now invite Francisca to continue our presentation. Thank you again.
We don't hear you, Francisca.
Yeah, I will continue for the interview. Sorry, we don't have any more presentation now.
Okay. So thank you very much for this presentation, and also the work that we've done. It was impressive and very complete. And congratulations again for having winning this preliminary design competition. We have prepared some questions for you. The first question we'd like to ask you. So you won the first Nanosatellite Challenge, which aimed to do lunar flyby. What was the most challenging part of designing a lunar mission? Is it very different from an Earth orbit mission?
Okay, exactly. So one of the tasks that we had to be more careful with was the propulsion system. Most of the time it's electric, but we chose a chemical one since it requires less time to travel, and due to this Van Allen radiation belt, which affects less the system. In comparison with an Earth orbit mission, we had to be more aware of the orbit maneuvers to perform it. Yeah.
Yeah, it was not very typical and quite challenging for a first challenge. I agree with you. And the second question we'd like to ask you, so your team was very diverse. You had members from 2 different institutions, from UB in Portugal and also UPM in Spain. How was it to work in an international environment?
It was very, very nice. We'll be able to practice our language, of course, because we always speak in English. But first of all, the fact that Jorge was in the Erasmus program in UBI, and our common interests in the matter created an opportunity to build a team and to share our knowledge acquired into different educational environments.
That was also a very nice point of the team, and we are very happy about that. So the last question we prepared for you: how did the Nanostar project help you and the student from your university to be more involved in the space sector? Do you see the institution continuing to develop more nanosatellite projects in the future?
Okay. Yeah, the Nanostar project awoke an interest in all of us when it comes to the space sector, first of all. And then, in fact, after the project, the members started their professional careers in the space sector, each one on the corresponding task area that we made on the project. First, for example, I was working with the CubeSats coating, and currently I am working in a company as a system engineer that requires knowledge about the aerospace materials. Other example is Jorge is doing an internship on HESA. But yeah, so at the moment UBI has several space projects working on rockets and CubeSats specifically.
Okay, yeah, we are very happy also on the outgoing related to the students that were involved, especially in your project, and also about the university project that will go on after this Nanostar project. Thank you very much.
Thank you very much, and congratulations.
Thank you. Thank you.
So I think, Filippo, we are going to announce the winners of the specific challenges, right?
Yes, this will be done by Carlos Romero.
Yes, hello, can you hear me?
Hello, Carlos. Yes, welcome. Do you have access to the presentation?
I'm about to give you the access, Carlos.
That's great.
There you go. Yes.
Okay.
And thank you very much, Filippo and Anthony, for your job on this session. And thank you to all the speakers and the students, and Xavier and Olivier as well for your presentation. Carlos, it's your time now. If you can move on.
Okay. Thank you very much. During last, let me check the control of the presentations. Yes, perfect. During last 18 months, the students from the Nanostar universities have been working on different detailed designs, analysis, fabrication, and test challenges. Almost all relevant areas of a complete nanosatellite system have been covered, with a total of 49 completed challenges. This morning, the best pre-selected 10 teams have presented their work, and the Nanostar jury panel has selected the best 3 teams. And here and now, I'm really excited because I have the honor of announcing that the winners are: in the 3rd position, the project called Design and Analysis of Nanosatellite Additive Manufacture Structures from Universidade da Beira Interior. In the second position, the project selected is Telemetry System Qualification from Bordeaux IMP University. And finally, in the 1st position, the selected project is Development of an Inertial Morphing Nanosatellite from Universidad Carlos III de Madrid and Universidad Politécnica de Madrid. All the participants, the best 10 teams, and the winners will receive a diploma, and congratulations to all of you. Regarding to the winner, as I mentioned, this amazing project, development of an inertial morphing nanosatellite from Universidad Carlos III de Madrid and Universidad Politécnica de Madrid. The team is composed by 6 students from these universities: Jesús Manuel Muñoz, Alberto Rodríguez Amor, Iván Castro Fernández, Miguel Segovia Mora, Carmen García Cabetas, and Carlos San Miguel Ortega. And we have here with us one of the members of this winning team, Jesús Manuel Muñoz, and I have some questions for you. Are you here with us, Jesús Manuel Muñoz? Yes? Oh, I can see you. Hi. Thank you and congratulations. You can transmit this congratulations to all the team. First question I'd like to do is, how do you feel now in that you are the winner of the challenge?
Well, it's an amazing feeling. Honestly, we've been working so much for Nanostar. All the hard work has paid off, definitely. All the days that we've been working overnight to have the project on time, knowing that we are the winners, knowing that there are more than 48 challenges already submitted, all of very, very high quality, is an honor, and I'm very pleased. And I would like to also say thank you to all the team and to other challenges for making Nanostar possible. It's an honor.
The level has been really high and it's very similar to the real life with the timing, etc. So congratulations. Could you describe your challenge in a few words?
All right. So what we are doing in this ACE Dynamics within the Nanostar collaboration is developing a new attitude control system for small satellites. And we are doing it from end-to-end approach, from simulations, CAD design, and all the theory and the investigation we are doing in this new attitude control system to an actual prototype and testing in laboratory conditions. So the novelty of our design is that we are using something called Basenev-Volkov effect, which is an effect that occurs in objects just by the way their mass is distributed within them. So by using this effect combined with current technology like reaction wheels, we're capable of saving energy and time. And this is an attitude control system that we would like to see in the future in the small satellites.
Wow, what you tell is not about a university competition, it's more a real life competition. Congratulations. Has this challenge provided you an add value to your training?
Yeah, and I think I can speak from all the team. As I said, this is end-to-end process. So from my point of view, I was not aware of most of the things that need to be taken into account when they're actually doing something in real life, like for example, all the electrical connections, the routing of the cables, everything is a challenge and everything comes with a problem associated to. So it's really, it's a really honor to be part of Nanostar. I have the opportunity to develop this project within this construction. And we have learned a lot from the electrical connection, how to design systems engineering, concurrent engineering, and from having something done in simulations and in computer-aided design to have something done in real life is a real challenge, and we have actually learned a lot.
Do you think that by addressing this challenge, you will have more business opportunities in the near future?
I think so, because everything started with an idea, and the first step was developed this in Nanostar, test that the prototype was suitable for real life conditions and for laboratory conditions, and at the very end we want to develop this in real space mission. And for that matter, in Nanostar we develop a space mission with our technology and a small prototype that will test that our technology can actually be done in a real space mission. So actually, thanks to Nanostar, the support and the confidence you have given to us, I think we are more and more closer to develop this technology in real life.
Speaking of your future, in what direction do you want to develop your professional career? I hope something related to space, but something more concrete. What are your expectations?
That's a good question. I like space technologies, and as Nigel has said before, I think we are living in a very exciting area of new space technologies. So I would like to keep developing this technology in the future. For example, within DCS Dynamics, we are planning to test this technology that we have presented thanks to Nanostar in microgravity conditions in a parabolic flight. So this is going to be our next step in October this year.
My last question, what would you like to say to other students to motivate them to participate in future challenges like Nanostar?
Okay, that's a good question. I would like to say two things to them. First, they need to be aware that Nanostar is a competition that will require time from them. So they need to be aware that they will have to devote time to it, to do something meaningful, to put something of high quality. And that's something that, depending on the schedule of the people, it might not be possible. So please make sure that you have time to do this properly and you have time to enjoy it, because if you don't really have time to do it, at the very end, you are not going to enjoy the experience. So I would like to say that. And in case you feel confidence to find the time for it, it will be definitely worth it. It's an amazing opportunity, not only from all the benefits that you can have when being in a team in a multi-international environment, but also being in contact with the experts for Nanostar, having the opportunity to have economic funding for your project, to make it a reality, and actually to present it to a group of experts is something that cannot be done otherwise. So please go ahead and enjoy the experience.
Congratulations! I really enjoy with this question, with your answers. Just to finish, you can find a brief description of each challenge on the website. You can then filter by university, etc. And I give the floor to Jorge Monteiro from Universidade da Beira Interior and to Maud Pierre Campi from Aerospace Valley, who will talk about parts for the future of Nanostar. Thank you.
Thank you.
Thank you very much.
Thank you all very much. And congratulations to the team.
Good afternoon, all. I'm Jorge Monteiro. I'm a researcher at the University of Interior. Maud here, that has been hosting the event. We are going to present the paths for the future of Nanostar. We will try to be fast and efficient as we are on schedule. So yeah, thank you for listening to us. So basically, this presentation will go throughout these main topics. So starting with the introduction about where we are at now, and going for the potential value and value proposition of Nanostar, what we can do in the future, and we will end with a call to action for all of you who wants to participate in this project, because we are looking into the future very actively. So about the Nanostar, so you have heard it already, so I will not go throughout so much about it, but simply it's a collaborative online platform to provide relative training on Nanostar technology throughout Student Challenge. You have heard about the Student Challenge already, and also about the collaborative online platform that Thibaut also talked about, but what we see is like if we focus on the Nanostar software suite, which was one of the major objectives of this project, we understand that we developed a suite of tools, open source tools, to aid the mission analysis and preliminary design of non-satellite missions. So these tools would be used for education and training. So there is a huge requirements that are associated with these tools. It needs to be open source, needs to be a really ergonomic and simple interface for the students, for the professors as well. And we also wanted it to be used as remote work. So even if the students and the professors are not together, they can use this collaborative platform. Okay. So now we are in the prototype phase. So we finished the development of some modules. We are integrating them. Some of them need more integration than the others. We are still working on that. But basically, we have a prototype, a web platform that is able to integrate open source tools in satellite mission planning. Our final goal, however, is to have an open source product. So basically, what we really want to do is in the final, we have a centralized modular collaborative working environment, which we can use via web platform and can integrate open source tools and expert tools regarding not only mission planning, but also project management, stakeholders, financial engineering, all of these tools we could develop and could be integrated in this centralized open source product. Okay, so for that we still need some next steps that we are planning to include in a future project. So basically, we need to test the tools and integrations better. So some of the modules, some of the tools were developed in the end of the project. So we need to test it again with the students, and the students need to use it. Also, you need to really ease the installation and setup process, as Thibaut was telling. Now we just have the installation procedure should be done by IT experts. In the final product, it should be done easily by anyone. Then we aim, this is a really nice point that we really aim to do in the future, is to produce tutorials and do more documentation on this aspect. So it will have educational training documents and even videos for the students to be easy, and for everyone could use it and could understand and use the tool. Then we want a seamless integration with all the modules. You don't really need to, at least with the educational models, you don't really need to have other Angular or Python, or you don't need to program. You just need to have a REST API. And then we want also to develop more modules, as I was telling you, for example, financial engineering, project manager, all of this, and integrate more open source tools that already exist in the market. So we just need to integrate them. Okay. This is for the technical side. Now let's check what is the need in the ecosystem for a tool like this and for a project like this. Okay, so if we have a look into the space ecosystem, it's growing. There is no doubt of that. So space access is now democratized, and there are small players that are coming along. So they are growing fast. We see that developing countries want to enter the space race. Also, startups, experts, and consulting services are growing. And you even see one thing that you didn't see until now, which is you see that people can remote work and can be like they don't need to work for a company to provide services. And consultants in the space area are growing a lot, which it's not so common because it's an area that usually was government backed up and was a big company backed up. So we have all these students, universities, experts, startups, and even organizations, non-profit, that they need tools that they can use for the mission analysis and planning of small systems, and maybe beyond that are open source, and you don't need to pay for them, which is not what is happening right now. There is a lot of tools that are really expensive. So that's the point two. So the new space panorama is challenging, and these players need to have these tools. So there is a lot of high costs. There is a lot of high specialized skills, and we need to put this together. Okay. And then there is a third point, which is education is theoretical. Most of the education now in the space sector for these small players like developing countries and all of this is very theoretical, so, and it's connected with industry needs. So we need to put industry and education more into each other, so more connected, and we need to really train professionals now, because the industry is needing now, not in 20 years from now, which is what we are really focused on in education. So there is a lot of STEM, but we need to qualify and train and give qualified skills and specialized skills now to the students. So basically this also we need to recruit and train these professionals, which are time and cost consuming activities for these small players. So this is why what is around the space right now. And if we look on how can NSS fit on this ecosystem, we see that most of the strengths are that it's an open source, as we already said, it's open source, it's easy to integrate. We can involve experts and professors around this tool, and also industry and academy. And we already have a proved formula for hands-on challenges. And these hands-on challenges, as you saw in the last presentation, they have been training students, and they give the students the hands-on education that they need to go for the industry. Then we have these opportunities that I talked to you about. So we need to qualify professionals. We need to do more hands-on education, and education needs to be more oriented to innovation and to business. Okay, so for the industry. For the tool, there is still some weakness and some threats. So the weakness is that it's very student oriented at this point. So it's simple. Okay, we can develop further, but for now it's a simple tool. There is no official support until now, and no funding for the next phases. That's something that we are actively looking into. So if you're interested, please reach out to us. We need to develop more documentation and tutorials, and it's in the prototype stage. For the threads, basically no funding, as I said, and there is competition from other tools that are paid. Okay. For the potential values of Nanostar, what we can do. So Nanostar is not only the tool, so we have a whole consortium behind it. This consortium has high level of expert in research and development, but also in education. So it's professors that are used to give education to the students and can use these tools to do more hands-on education. Then we have the state-of-art tools. We have the proved formula for hands-on education, and we have established a network already between us that will share resources, will share skills, will share all of this. This is what we want to build for Europe. Okay, so we want to build an established network that can share resources between ourselves. So the value proposition is that we can give online education and capacity building in space engineering on small satellites. So this is something that we can do with Nanostar. With Nanostar, we can organize educational hands-on and continue with these hands-on challenges, which were perfect for the students, as we saw. We can provide access to these tools and provide technical support and advice on those tools also. And we can also provide to the ones that are willing to join the consortium a network of experts and resources, and we can expand this network with your help and with your skills as well. So for the future, what we are thinking on today, and these are two ideas of our paths for the future, is one about Nanostar Academy and the two Nanostar experts. So those will be part of the Nanostar consortium and initiatives. And the first one, the Nanostar Academy, basically we wanted to develop full certified hands-on education in space project engineering to rapidly qualify professionals. So it will be a certified education course that people could go in, and this certification will give these students a whole new level of qualification. And then the Nanostar experts could be a network of experts that will be willing to provide technical support on NSCS, but also specialized knowledge around space engineering. So if you are an expert in, for example, attitude and determination and control, you could be part of Nanostar, and startups could, for example, pay for your skills, for your hours, or you could help universities on their CubeSat projects. Next one. Great. Nanostar Academy, to be more precise. So basically, is why there is certification of competencies and qualifications. So we would help also to recruit these professionals for the industry, which is needed. So if a startup sees, okay, this guy, this student has the certification for this of this course, so he already worked on nanosatellite projects, it would be awesome for them to recruit him. And also we can put industry, we can give industry a say on the educational plan. So industry could say, okay, our needs are those, so if it will be helpful if you could do hands-on challenges in this area for the students to learn more about this. So these are the really whys of the academy. So basically what we thought was to join all these three parts, so academy, industry, and even educational entities. So basically there will be the educational managers, which will be private entities or non-profits that could produce the events and organize the events, and then they will call the industry experts and the lecturers to give the presentations and to give the lectures, and also to work on the NSS, and then we can distribute these educational courses in certified stakeholders. So, for example, under Nanostar brand or under other partner brand. Okay. So basically, the revenues here could be educational courses, training materials, industry sponsorships, cross-selling products, and even the distributor brands. So that like the stakeholder that wants to develop these courses. Okay, could be industry, could be university, could be whatever. And then the Nanostar expert, why? Because we can have a network of experts that could be paid for their skills. So we would help the experts to provide their skills to users in need, so without the commitment. So they don't need to be employed by the industry. They don't need to be part of just one industry, one company. They could be paid by the hour. Okay. Then they could also give IT support. So we could have like some experts that are developing a tool and they can support on IT, on integration with other expert tools, for example. And then it would also be good for recruit and networking, because would be joining, will be connecting experts with industry, which would be helpful for recruiting them if there is the need for that. So basically here there will be the NSS managers, so the Nanostar managers, which will recruit even the specialists or the IT guys, and they will put them in contact with the industry or universities or research and development entities that are interested on these skills. Okay. So revenues here will be IT support, consulting, mentorship. So this is we need to still think about the revenue model and the organization model that could put all of this together and give value for all the parts involved. So basically, conclusion. So Nanostar mission is the open satellite project engineering to everyone. So basically, by training professionals and developing open source concurrent engineering tools for education and research, then NSS has a big potential to become a global open source platform for concurrent space project engineering. We have here a platform that we still need to develop further, but we agree that there is really huge potential here, and with the help we can develop this further, and then we can guarantee the sustainability of Nanostar community by creating services around this platform, the Nanostar software suite. We can help the academy, for example, and the expert, as I told you. For this, we need to recruit lecturers. We need to increase the network of lecturers, of organizations, of education managers, and for the expert, we also need to increase the experts, the IT engineers. We need IT engineers to continue to develop the tool, and we also need managers to manage between the organizations and the experts. Okay. And for final, Nanostar is actively looking into the future. So we are finishing now our project. And we will be working until the end of this month on defining a new project and the paths for the future. So if you are interested, please reach out to us, because we are doing this and we will be happy to come with our help. Now I will pass the words to Maud to finish this presentation. Thank you all for listening.
Thank you very much, George. I think you gave us a great overview of the future path of Nanostar, and as you were saying, we are still looking for a way of doing it and maybe new partners and see what is of interest for the new stakeholders. As you can see during this presentation, we had many speakers. It shows how this project touched the overall academic but also industrial aspects of nanosatellites. So after the end of this presentation that will come very soon now, you will have a pop-up coming up with 3 questions. So if you would like to be involved in the future of Nanostar activities, please complete this quick survey of 3 questions, and we will get back to you with more information about the project and see whereas you might be involved with us in the future of the Nanostar project. With this, I would like to end today the final event of Nanostar project. I will share with you the video presentation of the results of the project. So I'd like to warmly thank all the speakers. We were more than 25 speakers during these 2 hours and a half. We're sorry about the delay, but this kind of things happens. So thanks a lot to all of you, to all the speakers, to all the students that did an amazing job answering all the challenges. And of course, thanks to all the partners that were highly involved in this final event this afternoon.
And their efficiency for air recycling, which may one day play an essential role in the creation of artificial ecosystems for deep space exploration missions. From September 2019 to March 2021, more than 50 challenges have been organized among all the Nanostar universities.
Quand tu regardes ça, tu te dis, mais c'est trop bien alors. Ouais, c'est chouette. Non, franchement.
The future main players in the field of nanosatellites in a more connected Earth.